Chapter 3, Section 3.1, Laplace's equation, the introduction. All right, so the last chapter we spent trying to discover what the force on a particle was given static source charges that aren't moving. And we came up with a couple of equations. We found out, that's the wrong marker by the way. We found out that we could use Coulomb's law to create an electric field, which is 1 over 4 pi epsilon naught, the integral of r hat over r squared of the charge density over all of space. And that turns out not to be a very simple integral to solve. So we discovered Gauss's law, which basically says the flux of the electric field through a surface is equal to the total charge enclosed over epsilon naught. And that works for the most trivial cases, as long as there's some kind of symmetry. But you know, using Gauss's law, we can actually get pretty far. Then we talked about using, differential form of Gauss's law might be useful as well. So if the gradient of the E vector, the divergence of the E vector is equal to the charge over epsilon naught. Then we introduced the concept of the potential. We said the E vector is equal to minus the grad of some scalar field V, which is the potential. And you can solve for the potential with this simple formula of 1 over r rho d tau. And this is a little better than this one because, you know, A, you're not dealing with vectors, and B, now you just have you're just dividing by 1. You know, the integral of 1 over r is rather trivial to calculate. And most forms of the rows you're going to get, you know, lead to an integral that's pretty easy to solve. But sometimes this turned out to be pretty hard too. And you know, if only there was a better way to solve problems involving, you know, strange configurations. We're not going to ignore them because they are important. One of the problems is, now that you know about conductors, is that even the charge density itself can't be told ahead of time. So you have to have a way of deriving what the charge density is going to be. Anyway, so we can use Poisson's equation, Poisson, I don't know how to pronounce it, which basically says the Laplacian of the potential is just equal to negative 1 over epsilon naught times the charge density. And Laplace's equation, which basically says that in certain regions of space there is no charge, and so you can use this equation to solve for it. Now, Laplace's equation isn't useful, well, nothing's useful really, if there's no charge anywhere in the universe, right? In that case, electric field 0 everywhere, the potential is constant. But it is useful when you're interested in a certain part of space and you know what the potential is around it. And we're going to cover more about how this is actually useful. Okay, so writing this out in full form, we have d by dx squared of v plus d squared by dy squared of v plus d squared by dz squared of v is going to equal 0. And if you've taken a class on partial differential equations, you should recognize this. You should already know the name of Laplace's equation, and you should probably know how to already solve these. Solutions for this differential equation are called harmonic functions. You'll see why as we discuss them. This particular problem, you know, substitute V for something else and you're working in thermodynamics, or you're working in gravitational fields, or magnetism, or soap bubbles. And there's a whole bunch of different problems you can solve using this, the knowledge to attack a problem that looks like this. So this is going to be a fun chapter where we actually do a lot more math than you'd think, and we end up solving a lot more problems than you think would be possible. Hope you enjoy this. Thanks, bye.